This is the next video in a chapter on chemical bonding and molecular geometry. We are talking about nomenclature, specifically for ionic compounds. We introduced the basics in the last video, and now we're going to go in a few more specifics, starting with what to do if your metal element can have more than one charge. So this is for what to do if a metal element's charge is flexible. And I want to be clear, what I mean by flexible is not that that charge can change in a particular compound. It's that the metal can take more than one possible charge. So these are for elements that live in the D or F block for the most part. The transition metals don't have fixed charges like the main group elements do. And so the special rule for this one is that we know the metal element is going to be in the cation, but we don't know what the charge of that cation is going to be because there's several options. So we're going to spell it out by including the charge in the name in parentheses. And then we'll put a space, and then we'll put the anion with that "-ide" suffix. Scoot that over so you can see. There we go. So basically, we're trying to make the name as short as possible. And for normal ionic compounds, we don't have to list the charge because it's obvious what it is for any chemist who knows anything about chemistry. But for the case of the D and F block, we don't know what the charge is, so we have to spell it out in the name. And specifically, when we write the charge, we don't just write it as a number. We write it as a Roman numeral, because that's just how it's always been. And so chemists have decided to do it like that from now on. All right, so let's do some examples and implement our newest rule. Let's do the different iron chlorides. We'll go ahead and spoil it and list both of them here. So the reason we can't just name this iron chloride is that there are multiple versions of iron chloride. There's one with 2 chlorines, and there's one with 3 chlorines. And the charge on the ion is different, on the iron is different in each case, so we need to specify. So let's go through our usual process. Iron is our metal. We'll just go ahead and do it for both of them since we can see those are going to be the same. Chlorine is our nonmetal. And we can figure out that this is going to be an ionic compound because the large electronegativity difference between a metal and a nonmetal. This is going to be ionic, and this is the same element, so this one is going to be ionic as well. And so now we're going to have a look at the metal before we continue to check whether this is a main group or a transition. Let's see, here's iron. Iron is solidly in the center of the transition metal block. In the D block. So it's going to have a flexible potential charge. So before we can write the name, we need to figure out what that charge is going to be in each case. So this is something you can probably do in your head, do a little bit of mental math, but just so it's really obvious what that mental math looks like, we'll spell it all the way out. We know that the total charge of this entire formula needs to be 0. Remember, we said that was one of the ways we knew how to write the ionic formula, is that the sum of all of the charges should be 0, so the compound is neutral. So we know that if we take one iron compound with some charge that we don't know, and we add 2 chlorine atoms with a charge that we do know, the sum of those numbers, sum of those charges should be 0. We know the charge of chlorine is -1 because it lives in group 17, and that charge is usually the same, but we don't know the charge of iron. That charge is flexible. So we can solve this math equation, and we find that the iron charge is going to be 2+. So now that we know the charge, we're ready to write the name. So we write the cation, that's iron. Then we write the charge in parentheses as a Roman numeral. So left parenthesis, Roman numeral 2, right parenthesis, we leave a space. And then we write the anion, chlorine, and we change it to chloride. So now there's two interesting parts to our name. So pause the video and see if you can figure out how to name the next iron chloride compound. We need to take 1 iron plus 3 chlorines, and the total charge needs to equal 0. We know the charge of chlorine is -1. We don't know the charge of iron, and we can solve this algebra to find that iron equals 3+. So when we write the name for this guy, it's going to be iron, parenthesis, Roman numeral 3, chloride. So now, if all I had to work with a name, I would be able to tell which one of these two iron chloride compounds the name was referring to because of that charge. And speaking of recognizing what the formula looks like from the name, we haven't practiced doing any of those. So let's practice moving in the reverse direction. So moving from the name and words to the formula. So what we have to do when we write the formula is to determine the element ratio. Because the name doesn't tell us, right? The name has no indication of how many irons or how many chlorines are in this compound. So we have to figure it out, and we figure it out from the charges, the charge on each of the ions, because that's how we decided to write the formula in the first place, right? Was we just wanted to balance the charges of them. So we'll just go ahead with an example. I think we can do it. So let's do another iron compound. As our example, let's do iron 2 sulfate. So even when we're starting with the name, we still need to figure out if this is an ionic or a molecular compound or not. And what automatically tells me that this is an ionic compound is the fact that there's no prefixes indicating how many pieces there are. It doesn't say how many irons, and it doesn't say how many sulfates. So that means I must know information about these, and the only way that I know information is if they are ions. That will make more sense when we name the covalent compounds later. So if there's no number prefixes, then the compound is going to be ionic. So I look at iron, and I see that iron is a metal. And I look at sulfate, and I recognize this is one of the polyatomic ions that I memorized. So I'll go ahead and write the formulas as they are by themselves. So sulfate by itself is SO4 2-, and iron by itself is going to be an Fe, and its charge is going to be specifically indicated here by the formula. So it'll be an Fe2+. So I have 2 of those. And then this is just like the exercise we did when we first learned about ionic compounds. We take our 2 ions and we figure out how many of them to put together in the formula ratio. So we take our 2 ions and we take the charge on the cation and we put it next to the anion, being careful to leave that in parentheses so we don't mix up the number of oxygens with the number of ions. And we take the charge of the anion and we put it as the subscript for the cation. So we've got Fe2 and SO4 And remember that case that we said where sometimes you simplify the ratio if needed? This is one of those cases. So notice that I have both of my subscripts are 2, and I could simplify this by dividing them both by 2 and reducing them to 1. So I can reduce it to Fe1SO41, and I don't have to write the ones because I can leave them out. And you can write in parentheses if you like, but that's not required. So it's a little bit of a mystery how many of each ion there are in an ionic compound because it's not spelled out in the name. You have to do a little bit of problem solving to figure out how many there are. Okay, so we've talked about how to name ions and how to start from the word and go back to the formula. There's one more type of special compound that I want to introduce while we're here, because it's something that you often see written on lab bottles while you're doing experiments, and that's called a hydrate, which is something that has water molecules specifically incorporated into its crystal structure. So some ionic compounds include water molecules, H2O, in their lattice structure. So we talked about the lattice structure being a regular repeating pattern of cations and anions. There's extra space in between those cations and anions, and some of that extra space is filled by water molecules. And so we can measure how many water molecules there are per unit by mass, and we like to include that in the name. So when we write the name for a hydrate, we have an extra word on the end. So we write the name of the cation, as usual. We leave a space. We write the name of the anion with that "ide" suffix, as usual. Then we have a space and we have a third word, and we're going to put in the word hydrates. But we have no way of knowing how many hydrates we have because they don't have a charge. So we need to include a prefix to tell us how many hydrates we have. And those are going to be the Greek prefixes. Let's make sure we have enough room here. Okay, yes, we do. So let's make a little table of the first 10 prefixes, the ones you're likely to run into. You probably won't run into any crystal structures with more than 10 waters for a while. So this should be enough to do you. So we're going to use the Greek prefixes. Those are going to be mono, di, tri, tetra, penta, hexa, hepta, octa, nona, and deca. And technically they should have a dash next to them to show that they're a prefix. They go before something. So those are pretty straightforward, and we're pretty familiar with using those anyway. So let's go ahead and solidify that with an example. Now, when we have the hydrate, the chemical formula starts to look a lot more intense. You have the cation anion part of the formula. You have a dot that's centered vertically on the line. And then you have the number of water molecules placed afterwards. So they've emphasized that the water molecules are inserted into that lattice. So we can do the same thing that we always do. We're not afraid of hydrates. Here's sodium. Sodium is a metal, and it's a main group metal, so we know what the charge is. We don't have to figure out what it is. Then we recognize CO3 as one of the polyatomics. Specifically, we remember that this one is named carbonate. And then we can see over here the H2Os after the dot. That's called a hydrate. And so we can see here that this polyatomic anion is made up of nonmetals, carbon and oxygen. So there's going to be a large electronegativity difference here in this compound. And it's going to be an ionic compound. So we'll use our familiar ionic nomenclature rules. So we write the cation first, as is sodium, space. By the way, you don't have to write in rainbow colors every time you do this. I'm just doing this for emphasis. We put the name of the polyatomic anion as is. We don't have to add an ending to this one because the name carbonate already indicates what the charge is and that it's an anion. And then when we name the hydrates, we include a prefix to tell us how many there are. So there are 10 waters. So we add the word decahydrate to the end. So here's the exciting part, is the deca. So that's all the ionic nomenclature that you need to know for right now, how to go from the formula to the name, how to go to from the name to the formula, how to know when to include the Roman numeral and when not to include it, and to recognize how to add in that extra word when you have a hydrate. So in the next video, we will talk about how to name simple covalent compounds.